Okay, so simple DIY engine management. Just as a little bit of housekeeping to start off with, if you're here for any of these engines, you're in the wrong place. I'm actually going to be talking about these, which are engines in a car. For reference, by the way, there's a 45-year-old engine under all the mess there somewhere. Okay, things I'm actually going to talk about today. Engine basics, just so I can get a little bit of a feel for where to go with the talk. Who would say they understand how an engine works? Okay, cool. Who would say that they are comfortable with how fuel injection works? Okay. And who would understand what I meant if I said the term volumetric efficiency? Right, cool, that's fine. I'm going to be talking about the functions of an ECU or an EMS. So ECU typically being electronic control unit or engine control unit, or EMS, engine management system. The two terms are somewhat interchangeable, with EMS being the slightly preferred terminology for what I'm talking about today. I'm going to talk about the various sensors involved with an EMS and what I/O they perform. I'm going to talk about why Arduino is the best possible platform for a hacker EMS. I'm going to talk about why Arduino is the worst possible platform for any EMS. I'm going to talk about how to bring it all together on the cheap, so make it really accessible. And I'm going to do a bit of a demo and questions if the demo gods allow it. Apologies in advance if there's anybody out there listening from other EMS projects. That this is a bit of an aberration compared to what other people are working on sometimes. Okay, engines need managing. Yes, like us all, engines do need managing. The basics of a four-stroke engine are essentially that we need to get some fuel in, and we need to determine how much that fuel is, and we need to ignite that fuel at the correct time. It is mostly a math problem, so I chose a really good CPU for math. Determining the fuel requirements that we have based on the load and the speed of an engine, implementing the calculations required for it, and taking into account a bunch of edge cases, for example, starting an engine in the cold, acceleration, outside temperature. Sorry, let me jump back. Ignition and spark management. So this is the timing of a spark plug. This is actually more difficult than fuel management in a lot of ways. It's a very precise timing issue. And also running all the extra bits. So all the things that an engine needs to run, controlling a fan, controlling the idle, and protecting the engine in case of any component failures. So anyone who's ever worked with engines will probably seen a diagram like this. This is essentially running through the four cycles or four strokes of an engine. We take fuel in, the fuel is compressed, it's then ignited, and then we have an exhaust stroke to get the gases out of there again. There's two things going on here that you can see. There's a fuel injector on the left and there's a spark plug in the centre. At various stages of the cycle you can see both of those going off. It's the control of those which I'm going to be talking about today, and that's what we want to handle with an engine management system. All right, so why would you want to do this in the first place? It seems like it should be a solved problem. Well, back in the old days, we didn't have fuel injection, we had carburetors. They were, at best, an estimate to try and get fuel into an engine, and we had distributors, which controlled the timing of an engine. They did it okay, but they had a lot of limitations, particularly being mechanical. A fully programmable engine management system gives you total access to the fueling and timing of an engine. If it's set up correctly, you can have as much or as little fuel as you want, and you can make the spark go off whenever you want in that cycle. It's used primarily in race engines. An awful lot of race applications can benefit from this. And it's very common with engine swaps and conversions and things like that as well. The existing options out there for aftermarket engine management all cater to different audiences, none of which were what I really wanted to target. They were either too closed. Now the aftermarket engine or the aftermarket automotive industry is ridiculously closed and secretive. They're like a lot of IT vendors in that way, I suppose. But they don't like giving anything back, and they certainly don't like telling you how their products work. Some engine management systems, for example, are as limited as you can't set your own tune. You have to send it away. They put it on and they will send it back. Really not what you want. Too expensive. These systems can be easily up to $4,000, $5,000. There are lower priced systems with varying capabilities, but there were none as low as the area that I wanted to hit. Too complex or too simple. So when I'm talking about complexity there, I'm not talking about complexity to use, although that is another issue. I'm talking about complexity to actually hack on. So if you just want to play with engine management and go and get an engine running, that's fine. There are a lot of options for you. If you want to actually know how the system is working, it's a very, very steep learning curve in the few areas that will actually even let you do that in the beginning. And some are too simple. Some are just, turn the knob to make more fuel go in, turn it the other way to make less fuel go in. So we needed something that was going to be very hacker friendly, very simple, and something that people could actually learn a bit on. There's quite an overlap of interests in this area. A lot of car people are interested in electronics. A lot of electronics people are interested in cars. Sometimes they don't always know how to best work with each other. So this was a good project for trying to help people understand how the two can relate in what is really the heart of an engine control system. Learning as well was a big one. There's a really massive model engine market out there for building small-scale engines and running them. Those guys are desperate for fuel injection gear that they don't have to spend thousands on. So that was another reason why we're doing this. Projects like Formula SAE are all using closed systems at the moment as well. And, who wouldn't want a fuel-injected go-kart or a lawnmower for that fact? Virtually every person who's ever made an engine management system has a fuel-injected lawnmower. It just seems the way to go. All right, so the goal was a hacker-friendly and advanced engine management. I didn't want it to be too simplistic, with as low a barrier to entry as possible for under $100. I'm using Arduino. It's simple, it's cheap. Yes, it's limited in capabilities, but it does have what we need. All the code in this is compiled straight up through the Arduino IDE. You can have it running on an IDE on an Arduino within 30 seconds of plugging it in. It will all just compile and work. There is no assembly knowledge required. There are very, very small amounts of assembly in the code, but they are sort of black box, and you don't really need to know what they're doing. You need to know what they're doing. You don't need to know how they're doing it. It will require a little bit of background engine knowledge. If you can install an engine management system, you could easily install this. But if you wanted to hack on it, this is going to be a lot simpler than other options. But what it definitely isn't was just going to be a testbed device for something that sits on the bench. I really wanted something that was capable of running a car properly. All right, so how do we go about doing this? Obviously, you're going to need some inputs to control an engine. The absolute must-haves that you need are the engine speed. You need to know how fast you're going. In this case, that translates to RPM. Engine position. Now, this is relative to a thing called top dead centre. Back on the diagram that we looked at before, which is this one, you'll note that the engine's actually going through 2 revolutions in its 4 cycles. Top dead centre occurs when the spark plug goes off, essentially. There's a little bit of timing there, but it's basically there. Everything is relative, therefore, to that point. Engine load, so that this is basically a measure of how hard the engine's having to work, and I'll talk about that a little bit more later. And a few constants, so you need to know the engine size, the injector size, and what flow rates they're going through and that sort of thing. So those are the absolute must-haves. What you really should have to run an engine as well is the engine temperature, so you need to know whether it's ice cold or whether you're nicely warmed up. You need to know the air temperature of the surrounding air. As most of you would probably know, the temperature of the air will affect how dense it is, which affects how much fuel you're going to need to put in there as well. And an O2 reading. This is done by a wideband or a narrowband oxygen sensor, which is fairly common along all cars these days. Wideband becoming much, much more common. Now, widebands are an incredible piece of gear. If you ever look into how they work, it's simply phenomenal. But they essentially give a reading of how much unburnt fuel is left after it's gone through the 4 strokes.
So just a question.
Yes.
Your system at the end, will that be closed loop?
Yes. Yep. Not in the demo, but yes.
Don't mind just rephrasing questions so we can get to
Oh, sorry. The question was, is this system closed loop using O2? And the answer is yes. All right. So this is an example of what's called a crank angle sensor. It's one kind of implementation of it called a missing tooth sensor. The sensor here can be any number of things. It can be a Hall effect sensor, which is nice and simple. It can be a variable reluctance sensor, or it can be an optical sensor. What's essentially going on is this cog here, or this wheel, will spin around at crank speed. This gives you 2 pieces of information. Firstly, every time you detect a tooth, you can tell how fast the engine is going and calculate RPM from that. You'll also note, however, that there is a missing tooth here. Now, the missing tooth is very important in that also gives position information for the engine. You can detect when you've missed that tooth and then know where you are in the engine cycle. These wheels come in a number of different styles. You can have 4 teeth. They're typically known as a 4-1 or a 12-1 type of sensor. They range anywhere from 4 teeth -1 up to about 60 teeth -2. Obviously, the more teeth you have, the more accurately you can know where the engine is in its cycle. A 36 -1 tooth wheel, for example, will give you 10 degrees of fixed accuracy. Between those teeth, you're going to be estimating where you are in the cycle, or how far you are from the next tooth. A wheel like that is a 36 -1 wheel. Very, very common, for example, on Ford engines. They've been using them for a long time. Very, very simple, very, very hacker friendly once you have access to the sensor. This is sort of how they're set up. Once you set the engine to top dead centre, you'll be pointing at a certain tooth. If you rotate the engine so that the first tooth after the gap is now pointing at the sensor, you take a reading for what angle you're at, and you can know where the engine is after that. So, logging a sensor like that gives you a pulse train that looks roughly like this. The y-axis here is a measurement of how long it took between each teeth, as measured in milliseconds. In this case, it's a 36 -1 wheel. The pulses between each tooth are about 0.7 of a millisecond there. The long ones that you see are approximately twice the height of the regular ones, so you know that you've missed a tooth at that point, and you know where you are. Does anyone want to guess at what's happening in that picture? Sorry? Changing revs, yes, but it's happening in a very specific way. This is actually what it looks like when an engine is cranking. And every time these go up, you're hitting a compression stroke, which makes the starter motor slow down. You've got to be really careful, obviously, not to put your missing tooth, right in the middle of there, because it becomes very hard to detect at that point. So in the 4 strokes, one of the strokes is compression, where the engine is compressing the mixture that you've got in there. Now, when you're cranking an engine on the starter motor will be applying a fixed amount of force. So when it gets to that compression stroke, it has to work harder and it will slow down. So that's why you get this kind of waveform. Okay, so load methods. This is essentially a way of determining the amount of air that's entering an engine. There's a number of ways that you can do it, and that manufacturers have done it in the past. There's a mass airflow sensor, a throttle position switch, and manifold absolute pressure are the most common methods. I'll talk about each of those in just a minute. MAF was traditionally used very early on in electronic control systems. It went through a bit of a heyday, faded out a little bit because it had a lot of weaknesses, starting to come back now